Well friends, I start with the introduction of the control problem which you are going to solve as a control engineer. I intend to devote 2 lectures to this. In today's lecture, I will concentrate on control system terminology. In the second lecture which is going to follow, I will give examples of control systems, many of them very well known to you, and some of them you will be coming to know later. So, we start with today's lecture which is on control systems terminology. Well, as we know, today control systems are playing an important role in development of modern civilization and technology. Every system we come across today, you see, has some type of control engineering involved in it. Take for example, a home heating system, a refrigerator, an air conditioner, an automobile, all these are examples of control systems. Take any sector of industry, you will find control systems everywhere. Say inventory control of manufactured products, automatic assembly line, machine tool control, well, the space technology and weapon systems, the robotics, the power plants, all are these the industrial sectors where you find control systems applications and the role control engineers have to play there. Well, feedback control theory principles have been effectively utilized in problems like inventory control, socio-economic systems as well. Our course is going to concentrate on the so called engineering system, wherein the physical system to be controlled obeys certain physical laws. The socio-economic and biological systems coming under the area of cybernetics we will not be able to handle in this course. Let me come to the basic terminology used in control systems. The system to be controlled is given different names, the most common being a process or a plant or the controlled system itself. In process industries, particularly chemicals, petroleum, steam power, etc., there are applications where we require the control of temperature, pressure, liquid level in vessels, humidity, composition and the like. All these applications have been referred to as in the literature as process control applications. Actually, the application of the control techniques, historically speaking, started in the area of process control only. This is typical of 1900 to 1940 era. During the Second World War, the need of automatic airplane pilots, the gun positioning systems, let me write for you, automatic airplane pilots, the gun positioning systems, radar antenna control systems, and the like were felt. To solve these problems, theory of servo mechanisms was developed. Theory of servo mechanisms. Note that the word servo mechanism originated from the words servo, means the slave or the servant, and the mechanism. So, it means a servo system is a system which is slave to the command, and this was the requirement of the weaponry system during the World War II. Well, the theory of cybernetics, the theory of servo mechanisms, the process control, all these are converging now, and a unified feedback control theory has emerged. and the terminology I am going to refer to is the terminology of unified feedback control theory, meaning thereby it is applicable to all the three subfields I have mentioned. So, in the basic terminology, let me first take up a block called the process, or as we have said, it could be termed as the plant as well, or a controlled system. The output of this particular process, I will name this as the response variable. The variable or the attribute of the process you want to control, and this control will be exercised by what I will refer to as the manipulated variable. The manipulated variable is subject to control by the controller we are going to design, and the requirement of the control is that there is unavoidable and undesirable disturbance acting on the process. This point may be very carefully noted. The disturbance is uncalled for and it is beyond your control. The disturbance may be originated outside the process environment, or the disturbance may also be originated from within the process. For example, the parameters of the process are subject to change with time. You have designed a controller for specific set of parameters, but with time these parameters may change, and hence your controller will not be as effective as it was at the time of its design. So, this is a disturbance on the process originated from within. There are examples, I will give you many examples of systems, and the examples of types of disturbances acting on the system will also be given. However, this point may please be noted that this is a signal which is beyond your control, which is random in nature. The characteristics of this signal are unknown to you. The manipulated variable is the variable to which the process is going to react, and the reaction of this process to the manipulated variable is going to make the response variable follow your commands. So, it means naturally speaking the manipulated variable must be under the control of the controller. So, I can put a block over here. So, it means there is a controller here. This controller is going to control the manipulated variable, and the function of this controller is to make the response variable follow the system commands. So, I think I can draw a neat block diagram now defining all these variables. Here I have a process, the output of the process, the attribute of the process under control may be referred to as the controlled variable. Here I have a manipulated variable, here is a controller, and the information given to this system, let me put it this way, is the command signal. These terms will be very frequently used in the SQL and therefore must be very carefully noted. This is the command input to this system, and here I have the disturbance. Though the disturbance has been shown schematically as if it is coming from outside the process environment, this again I will like to emphasize that it is an attribute, it is a signal which may be generated from within the process as well. The parameter changes is a specific example. Now, in this particular case, the requirement of this particular system or the requirement of this controller is to force the controlled variable follow the command in spite of random unknown disturbances acting on the system. Now, let us take the schemes, the possible schemes which can achieve this objective. One of the possible schemes, the simplest possible I will say, is the following. Take the process here, or let me write the plant now. This is your controlled variable and here is your manipulated variable. Let us say that the controller directly gets the information about the command signal from the user. This information which the controller gets from the user as a command signal is effectively utilized by this controller. The controller acts upon this signal to generate a manipulated variable whose function is to force the controlled variable follow the command. So, in this particular case, the only information available to the controller is the command signal. Now, please note this point. What is the problem with this type of structure or with this type of scheme? Let us say that the plant information, this controller was intelligent about the plant information at certain point of time, and a controller was designed to realize the objective of the controlled variable following the command signal. But in due course, if the disturbance onto the plant changes because of the reaction of the environment or because of the changes within the plant, what will happen? Your controller is ignorant about those changes. It means the controller, which was designed earlier for a specific information about the disturbance, is no more effective in making the controlled variable follow the command. So, it means there will be an error between the controlled variable and the command signal because of the changes in the disturbance variable. And hence, this type of controlled structure, which in the literature is referred to as open loop control. This term is the standard term for this type of control structure, an open loop control. The open loop mean that the loop has not been closed to give you the information about the controlled variable. In the next slide, I am going to give the closed loop control, wherein you will see the controller is intelligent and it gets information about the current status of the controlled variable as well. So, in this particular scheme, you say that if this random effect comes on the process, in that particular case the controller becomes ineffective to track this particular disturbance or to take action so as to nullify the effect of this disturbance on the process. So, what we require? We actually require that our controller should be more intelligent. What is the intelligence required? The additional information the controller requires is the disturbance. It should get the information about the disturbance also, so that it knows that in spite of that disturbance, the manipulated variable is to be manipulated, is to be controlled, so that this variable follows the command. Now, actually this is a random signal. Giving information to the controller about this signal is difficult. So, what is done in the process? Let this signal affect the plant. So, the effect of this particular signal on the plant will appear on the controlled variable. So, in that particular case, what I do? I take the plant here. This is your controlled variable. Here is the disturbance acting on the system. This is a manipulated variable, and here is a controller. Command. So, this controlled variable now, well, this can be measured easily, and there is a sensor here. This particular sensor gets the information about the controlled variable and passes on this information to the controller. So, you will please note that controller is now intelligent. It gets the information about the disturbances indirectly through the controlled variable. It does not get the information directly in this particular feedback structure. Now, the function of the controller is the following. It compares the actual controlled variable, the information available from the sensor, from the command signal, and generates an error signal, and that error signal it utilizes to generate a suitable control signal, and that control signal manipulates the signal to the plant so as to reduce the error to 0. So, this particular system is an error self-nulling process, wherein we find that the error between the command and the actual variable is reduced to 0 because of the controller action. This particular system in the literature is referred to as the closed loop system. The name is evident from the structure of the system, or it is also called a feedback control system, and we will be mostly concerned with this particular feedback structure. Now, look at the problems we are going to face using this particular structure. You see that the major source of the problem in this particular structure is the sensor itself. Recall that in the earlier structure on open loop control, the sensor was not there. This is the additional hardware you have introduced in this particular structure because of the requirement of making the controller more intelligent. Now, this sensor, when this piece of hardware is introduced in this particular loop, it is going to introduce problems of noise. So, you see, in the process of measurement, it generates high frequency noise, and this high frequency noise also gets injected into the loop. So, the plant and the controller, in addition to getting the useful signal about the command signal and the controlled variable, gets this noise signal, which is a high frequency signal, and the plant will react to that signal as well, and your control may not be effective. This particular problem was not there in the open loop structure. However, suitable noise filter can be installed in the loop, so that this particular problem of noise can be taken care of. Okay? Now, once we say that the noise problem is taken care of, then let us see what is the requirement on the controller. The requirement on the controller, I will say, is to make this particular system robust. The word robust is used in the control literature to emphasize the need of control, so as to make it insensitive to disturbances and parameter variations. So, if in spite of disturbances in certain range and the variations in the parameter of the plant, the controlled variable is able to follow the command signal accurately, in that particular case we say that the system under control is a robust system. It is giving robust performance, and the requirement of the feedback structure, one of the primary requirement of the feedback system, is to make the control system a robust one. Now, you see that you will like this controlled variable to follow this particular command very accurately. That is, the error between the controlled variable and the command signal should be minimized, and in addition, the follow up of the controlled variable to the command signal should be as fast as possible. So, it means accuracy at steady state, speed of response, and the other requirements are the primary requirements put on the controller. Now, as we will see later, that one of the disadvantages or problems associated with the controller with the feedback structure is this, that as you increase the requirements on system accuracy, there is a loss of stability. So, it means there is a trade off. There is always a limit to the accuracy which you can achieve. However, reconciliation of these requirements on system accuracy and stability is the primary accomplishment of feedback control theory, and the design of feedback control is concerned about this reconciliation, and we will see methods how a suitable trade off between the system accuracy and loss of stability can be accomplished. Now, you see that there are problems with the feedback structure we have referred to, but in spite of these disadvantages, the basic requirement of robust control make the feedback control systems almost indispensable. This point I will like to make it very clear. But for the requirement of robustness, but for the requirement of filtering the disturbance effects, feedback control structure would not have been required, because open loop control structure can meet the requirements of system accuracy very effectively. The problems of feedback control can be avoided But however, this structure, as I mentioned, is indispensable because of the requirement of filtering of disturbances and the effects of parameter variations. Now, let me come to the design aspects we are going to use. So, in this particular feedback control structure, let me come back to the same diagram. So, the design is that of the controller. Now, how to design this controller? There are various approaches which are possible, and some of the approaches I like to highlight, and I like to mention as to which is the specific approach we are going to follow in this particular course. One approach could be the experimental approach, so called the experimental approach. In this approach, what I do is I install a controller based on the experience, practical experience on the process of the plant. This particular controller which I install, there are certain parameters of this particular controller which I can then adjust online and see and get the parameters, so that the controlled variable is follow the command to an accuracy acceptable to the process engineer, acceptable to the user. This particular experimental design in the literature is referred to as the controller tuning. This is a method which is extensively used in process control applications, because the requirement there, one, the information about the process is not available so as to model it accurately. It is a highly nonlinear process model, and therefore, instead of relying on the quantitative information about the process, we rely on the experimental knowledge about the process, about the operator's experience about the process, install a controller and then tune the parameters of the controller, so that an effective tie up between the controlled variable and the command signal is achieved, a process known as controller tuning. And I may say that this is nothing but an ad hoc approach of design, an ad hoc approach. Now, let me take the other approach which I call as the model based approach or the analytical approach. In this particular approach, why do I need this approach? For example, if the requirements on the control are high, or if the system is too complex to be tuned using the ad hoc approach, in that particular case I will like to go for the model based approach. So, what I do in this particular approach, I capture the dynamics of the model in a suitable mathematical form, maybe a differential equation, a transfer function, or a state variable model. A suitable mathematical model is formed which captures all the important dynamics of the system quantitatively. Now, once this mathematical model is available, we are more knowledgeable about the characteristics of the system quantitatively, and this quantitative information is used to design a controller using analytical methods of design. So, once I design such a controller using analytical method, I hope to get, and I do get, better control on the system. And the third method, let me say, is the knowledge based approach. Is under the stage of active development, particularly during the last decade. This particular approach has become quite effective and quite useful in industry. Many industrial applications have used this knowledge based approach. As you know, in this approach we have what is called the expert control. We place the expert, the operator, in the loop through certain qualitative guidelines, certain qualitative rules about the system. The fuzzy control, the neural networks are playing an important role in this particular field of knowledge based control. And in this course, we are primarily concerned about the model based control. So, it means the approach will be for a physical system which is our plant, we are going to derive a mathematical model first. A mathematical model may be derived, as you will see. These are the approaches we are going to study in this particular course. This you can derive using the physical laws or using the experimentation. Using the physical laws of physics, we are able to capture the dynamics of the system in a set of differential equations, which can later be transformed into a convenient model like a transfer function or a state variable model. If this is not possible, alternatively we conduct experiment on the system, get the input output information, and this input output information is captured into a suitable differential equation or a transfer function model, a field referred to as system identification in the literature. Again, let me mention, in this particular course we will be primarily concerned with the modeling using physical laws. The other field will be outside the scope of this particular course, though it is quite important from the point of view of practical applications of control theory. Now, coming to the model based control algorithms, I will like to mention that during the 1940-1960 era, during this particular period, the frequency domain design methods were developed. Some of the techniques developed during this period, particularly during 1940 to 1950 when theory of servo mechanisms was developed, are the Nyquist techniques, the Nyquist stability methods, the Bode plots, the root locus plots, in the literature. These methods, the frequency domain design methods, are referred to as the classical methods of design. Well, if these methods are classical, well, there should be some methods which are so called modern. Well, the requirements of space vehicle control, well, the launching, the maneuvering, the tracking, this led to a theory which is based on state space techniques. So, let me mention over here that state space methods of design came into existence during 1960s onwards, and this particular domain of design has been referred to as modern control design. Well, you may say as if the earlier methods of frequency domain, they are classical, they are no more in existence, and the so called modern methods of design based on state space techniques should be in existence today. Well, it is not the situation. In industrial control applications, effectively 75% of the industrial control problems today are being handled using the classical methods of design. So, as such, the term modern control design is misleading. It really came into existence from the particular requirements of tracking in space vehicles. So, in the industrial control, it is still the classical method of design are still in existence and are being extensively used. Rather, it is being debated as to which methods of design are more robust, robustness being the primary requirement, whether the classical control methods or the modern control methods of design. So, I think let us give up this terminology of the classical control and the modern control methods. For this particular course, I will like to concentrate on, or rather this course will concentrate on the frequency domain methods of design all through. The state variable methods will be introduced in this course, not from the point of view of the design, but from the point of view of system simulation. As you will see that system simulation is effectively done, is conveniently done when the state variable formulation is utilized, and therefore, an introduction to the state variable methods will be given in this particular course from the point of view of system simulation. Now, with this terminology, I think we can go now to the control system basic structure, and to define the control system basic structure, I will like to give you the examples of control systems which we see in our day to day usage, or which you are going to design later when you go to industry. Some of the examples I like to take here. Well, let me take a very well known example of a feedback control structure. A bathroom toilet tank, I will prove to you, is actually a feedback control example. Let me take the example of an automobile driving. An example of residential heating. I will take the example with you of hydraulic steering mechanism. All these are the examples which are very well known to you, but we will put them into the control system structure. In addition, the steering control or the servo system for an antenna, and a speed control system will also be given as an example here. Through this example, the variety of control variables will also be illustrated, and in addition, I will give a basic control structure in which you find that all these systems will properly fit in, and I intend to take up these examples in the next lecture. Thank you.